also the green function integrated over time, and this has two components, as we saw. One, which is just what you would get anyways if you didn't have M0 to begin with, the vacuum component that we call it, and some other thing, I call it R now, or the rest, which depends on M0. Okay, so this is what depends on the choice that you made up here. Okay? So these are just the general formulas. And we wanted to see now more precisely how the different M0s and the different settings give rise to different dynamics. Okay? So the first setting that we saw is the one on the torus, where we said you can basically ignore whatever happens here if you know that your M0 is sufficiently nice. Sufficiently nice meant smooth, rapidly decaying to the Fourier side and Penrose state. Okay, so regular Penrose state. Let me abbreviate it. Okay, so this in particular tells you that in that setting, whatever your M0 is that you consider, as long as it's part of this class of backgrounds M0, equilibria M0, you don't see any particular effect due to them. You just see what you would see if you had vacuum, and this is the phase mixing dynamic that we saw free transformation. Now the story is different on Euclidean space, and I don't really know so much about general Euclidean spaces, so I consider myself to the case of 3 dimensions, which is also the, I guess, most physically relevant case. And then we looked at one particular example. This was this Poisson equilibrium, which is sort of relatively slowly decaying, but it has a nice Fourier transform. It's just e to the minus k as a Fourier transform, so you can compute everything that's here. In particular, you see that the green function has the same structure. Of course, it has something that is just due to the vacuum and something that is due to what you have in 0. And the interesting feature is that this combines 2 aspects. This combines, on the one hand, decay. I think this is for every frequency decay of your space, it's just RD. You get some exponential decay, and you have oscillations. Okay. You can plug this into the formula here and write down what you get. Just for the sake of diversity, I wrote it down in the physical space variables. And you see that, of course, one piece is given what you would get as your right-hand side. So the object that you started with, let's say you're coming from initial data. And then some other term. And this other term by now is not something negligible. It's something that, well, it has the same kind of characteristics, right? So it has oscillations. And it has decay. So this is the notation for the half-heat semi-group. So this convolution again is something that corresponds to. Okay. Is that picture clear? So it's a very specific case where you can write specific formulas and you see what's happening. And of course the question is how representative is this of general dynamics, right? So it's clearly very different from the case of the torus, but is it also otherwise meaningful example? Okay? So you can generalize this, and in fact, this computation gives some idea of what you could, how you could understand more general equilibrium. For example, one thing that you can do is to consider products of such functions, so higher powers of these functions, pseudo normalized. Then you know that products of these functions will just be convolutions on the Fourier side, so again you can compute things somewhat explicitly. Okay? So this MP is sort of part of a larger class of explicitly computable examples. And these examples, at least for us, have been very instructive in understanding some of the main features of the Leibniz dynamics here. So this is, you can look at these computations, wrote them up in some review article, showing with that bibliography. So this is something from last year. But so to give you the right idea, there have been, of course, many works trying to understand this in general three-dimensional space. There have been works by Petrovsky and Masnouchi and Nouveau in 2020. And by Antoine and Nguyen in 2020, aimed at understanding the dynamics near Maxwell lengths. For, let's say, much more sharply decaying equilibria. So, for Maxwellians, or sharply, rapidly decaying at 0. And so together with this review article, I think now we have a reasonable understanding of somehow the general class of dynamics in the dimensions. Okay? So there were specific works focusing on these settings, which basically try to get at the kind of statements we find in the physics literature. But in general, the picture is the following. So for a suitable class of such M0, meaning they should be reasonably smooth, they should have some features that allow you to apply complex analysis, so they should be somehow locally or morphically extendable. You can basically distinguish the dynamics in two regimes. One is the large frequency regime. So this is the case where you have, let's say, large frequencies, which is somewhat reminiscent of the torus case. This is the case where you have some sort of scattering frequencies. And in this case, your real function is basically just the delta plus some deltas. It is like the vacuum, it is like the torus. It should not be surprising because it's for large frequencies. As we saw yesterday, the whole difference of all these things with the fingers of every thing and so on is for small frequencies. So in the small frequency regime, you have now a new dynamic. You still have the vacuum, it has to be there, right? So that's a delta function times 0. But then there's a new component. We're going to simplify it a little bit, but essentially it's something that oscillates and decays. Right? So it's e to the I t omega 1 of k, and e to the minus t omega 2 of k. K is the frequency, and here omega 1 and omega 2 are real valued functions. Omega 2 is non-negative. And errors. And well, you can quantify this much more precisely. Okay, so understanding what exactly these functions look like is part of this lemma. I don't want to get too much into technicalities, but just to point out that you have again some sort of oscillation dynamic. Roughly speaking, you can say that this one function is something like 1 plus order of k squared, and the omega 2 function, well, is omega. Okay? You can say much more precisely what omega 2 is, but the main point is that omega 2 is smaller the thinner time 0 is. in other language, maybe you would call the combination of omega 1 plus omega 2, you call omega, which is omega 1 plus I omega 2, the dispersion relation of everything, zero, some linearized equation, right? So this could be something like the dispersion relation. The overall dispersion relation is imaginary real part, but dispersion relations may be a little bit misleading in the sense of what kind of dynamics they give rise to. The omega 2 gives just a damping dynamic. This, in general, is a dispersive dynamic. Right? So this is something that oscillates with a frequency that depends on the frequency scale. So this is what you would classically call a dispersion relation. These kind of functions you see in the Schrödinger equation, so this would be something like the square of the Klein-Gordon dispersion relation. These are really dispersive waves. Okay? So, and maybe as pictures, the case that I drew first is this NP, where you have that omega 1 of k, so the oscillations are just with a fixed frequency 1, and the omega 2 of k are of size simply k, right? So this is the e to the minus k, plus minus I. And then if you make things more narrow, let's say you consider what is the square of this p, let me say so, just the power of the first product of this function and p with itself, so something that is much more localized, which is a much thinner tail, you get that omega 1 of k is 1 plus k squared plus some remainder, and omega 2 of k is k to the power of 3 plus some remainder. So you see that you start having modes where the different frequencies wiggle at different velocities, and the damping gets weaker, right? We're in a regime where k is very small. So if you have damping at rate k, it's much stronger than damping at rate k cubed. The particular case that Lambda analyzed and sort of had some conjectures about is not also completely understood, so we have Maxwellians. So this would be Maxwellian. Then you have the same kind of form of omega 1. But omega 2 is something incredibly weak. So it's an exponential of e to minus 1 over k squared. So if k is very small, this can basically ignore this. So it's something incredibly small, so the dissipation you get is incredibly small, so that's why when Landau started all of this, it wasn't so clear that it would be real thing in experiments, whether it's something that's real or it's just some singularity of some integral that, okay, yeah, it's just a mathematical, right? What's the interpretation? Why is there this kind of relation? Now we get into something that you'll see maybe more than once today, some vague heuristic. And the idea is that this is due to this kind of particle wave interaction. So in the plasma, in your electrostatic plasma, you have lots of particles, so this continuous description of particles, and they're moving at various velocities, right? This tells you how many particles you have moving with what velocities. And at the same time, you have some wave, which is the wave at that macroscopic scale, the wave that is created here, is density wave. And this wave and these particles interact. And so you have something where, let's say you have some macroscopic wave. This would be the wave. And the point is that this wave can interact with particles. So let's say this is the speed of the wave. And if you have particles that are traveling at the same speed, then you can have an exchange of energy. So if you have basically, the claim is that if on average you look at some wave with some velocity, if you have many particles that are traveling much slower than this wave, the wave will lose energy to these particles. If there are many particles that travel much faster, then it will push these particles. It will push this wave. So roughly speaking, this tells you that if you want to have a lot of damping, if you want to have the wave that is being damped a lot, you should have a lot of particles at high frequency. So a lot of damping for this kind of flat rotating objects. Okay. Now in the physics literature, you often find examples of pictures like this, where they say electron surfing waves. This is supposed to be a more general object than in other systems. And you see a lot of pictures of what are supposed to be electron surfing waves, but I didn't find any really convincing electron surfing waves. On the other hand, what you do find are lots of pictures of ducks. Okay? So, this is the last lecture, so we can be a little bit more flexible with mathematics. This is from Ig Nobel Prize in 2022. So it's actual science, but maybe of slightly obscure type. But it illustrates to some extent the same idea. Okay? So the idea is that you have some wave. In this case, it's the wave of the mother duckling. Right? And you have a bunch of particles, many more than the wave, namely a bunch of ducklings behind. And these ducklings are surfing the wave. And the question was, in this Ig Nobel paper, how do these ducklings arrange themselves compared to the mother? And the idea, what they claim to demonstrate, is that they arrange themselves in such a way that they gain energy from the wave. In other words, they damp the wave that the mother creates for the sake of gaining energy themselves. Okay? So in this picture of the wave, the ducklings position themselves not on the crest where they have to push against the wave, but slightly behind the top, so that they get pushed by the wave. And this is illustrated in these graphics B, C, and D, where the mother creates some wave, and then you see in the reference frame of the ducklings, C and D, you see how they position themselves with respect to the wave, and the claim is if they do it in number E way, they're better off, and they can follow the much stronger, much faster mother, despite being much weaker and much slower themselves. Okay? So I hope this supports a little bit this claim that lambda damping is something much more important and universal than this particular thing. Illustrated also here. Right? So this is the same kind of thing, this chain of ducklings, and in particular, I think in this Ig Nobel work, they ask themselves how much energy can they gain, and the claim was something like 20% energy can be saved for the ducklings, and the wave at the end behind the last duckling is really much, much smaller than the beginning. Okay, so Ig Nobel Prize. So Ig Nobel Prize, right? Not Nobel. Okay. Good. All right. So much for the statement. So this is the claim of what is the mechanics behind this. Now, to make it mathematically rigorous, of course, is much less pictorial story, and this is the best version I think I can present in any sort of detail. Okay? Good. So let me emphasize there's a different dynamic between the toys. You see these kind of expressive effects. And okay, so now I can actually get to I think what Christian asked me last time. What is lambda damping? What is nonlinear lambda damping? And so on. Okay. So finally, let me say a few words about nonlinear results. My count is right. Okay. So there's one general caveat, which is basically this question of lambda damping, and the naming of it has this history where at some point lambda damping maybe meant just stability of some object. Okay? So you find a lot of papers that say lambda damping of something, and what it means in terms of mathematical statement is some nonlinear stability result. Okay? That's why I was a little bit careful to not use it for many other things, but the mechanism behind lambda damping results in the literature can be anything from phase mixing to dispersion to actually these things. Okay? But there's not so many results of this type. And this is somehow what one would like to, I guess, better understand still nowadays, which is still largely open. But so the rough overview of the history, let's say, of nonlinear results, maybe it would be preceded by some general thing about physics, right? So Lambda's original paper is in 1946, where he made these computations, but there was so he made a computation that suggested that you should have this behavior here. It wasn't quite, he couldn't really get this exponential, it wasn't great what exactly it should be, but he computed that it vanishes to any order, basically. So higher stuff, better, higher ranking than any polynomial. That's great. There were so many good examples left. So then this was sort of not really followed up by any experiments at the time. There weren't so many experiments. And I think it took something like 15 years for it to be studied a little bit more. One thing that sort of casts, that puts some prominence but also casts some doubt on it is the paper by Bernstein, Green and Kruskal, which constructed, so it's a physics paper, which constructed exact, so-called exact nonlinear plasma waves. So they constructed a family of exact solutions to the nonlinear equations. These are so-called DGK waves. These are basically constructed by creating certain trajectories for the underlying phase space distribution F in such a way that particles go around, they're trapped in certain potentials. So they constructed these exact nonlinear solutions, and I think they were also the first ones to call the phenomena observed by lambda lambda. And they said, well, these solutions do not have it. These solutions do not lambda them in the setting here. Actually, solutions are also set in the periodic case, so it's a little bit more murky in terms of what exactly it means. But they're very hesitant to claim anything too strong about what these solutions are. In particular, they said something like whether these solutions will be physically relevant and observed will depend on other factors that are ignored in these works. So they were not really adamant about saying there's no such thing as lambda damping. Okay? Thus created these exact nonlinear solutions. So, and they said no lambda damping. So it was not so clear that this lambda damping was working to begin with. It was only in 1965, 4, so when the fusion research really started, that Malmberg and Dorton, they did some experimental confirmations of lambda damping. Some experimental. Check whether there is some damping that you can measure these waves, and it turns out that yes. Okay. Despite this, I think it's still from somehow in a non-mathematician, in a general physics perspective, it's still largely unclear what should happen in general to the general dynamics, right? Because you have many these kind of exact nonlinear solutions, and there are many conjectures of what happens if you take a Maxwellian and you perturb it. Even I think in the physics books that I do, that you'll find many conjectures that would say, okay, you start maybe with a little bit of damping, but eventually you get close to one of these things. And in some way, these nonlinear solutions may be general attractors. There's many simulations that suggest that these objects play a very important role. But this is not at the level of mathematics statement, this is at the level of somehow the general dynamics, which are, I think, completely understood. Precise mathematics results. Now, for the mathematics, again, I divide the story into the confined case, the unconfined case. So, in this, I think people were wondering, well, are there any solutions that actually are nonlinear solutions and exhibit this lambda damping, right? On the torus, this lambda damping, as it's written up there, may just be the free transport. So nonlinear stability results, where you have solutions that are asymptotically free. the first result there is by Coyote and Maffei in 1998. And they constructed a class of solutions which actually are nonlinear solutions, but you have a convergence back to the equilibrium starting point. So you get a class of analytic solutions, some construction of analytic solutions near Maxwellians, which, well, let's say, for which the perturbation phase makes So they took some class of perturbations of Maxwellians on the torus, and they asked themselves, can I construct solutions that asymptotically exhibit this phase mixing that we discussed? So behave asymptotically like a free transport equation in the sense that you converge back to the Maxwellian kind of freedom. So they showed that this is possible. So they showed that it's perfectly possible to have nonlinear stability results that are somehow related to this kind of dynamic near equilibrium. It was generalized in 2007, 2008 by Juan and Velasquez. About a class of, let's say, roughly speaking, similar questions. And so the point where really I think this topic of lambda damping became very popular was the work of Moore and Milano in 2009. Okay. So instead of looking at this so-called final data problem, so instead of constructing certain solutions that display the behavior that you prescribe, they showed that starting from some perturbation forward in time, you get the signal pitch. Okay? So they showed that small, highly regular perturbations of, again, smooth and so on, Penrose stable equilibrium, behave in the same way, namely are phase mixing free scattering. So lead to global solutions, nonlinear solutions. So the perturbations phase mix. Meaning again the free scattering of the perturbations, and you convert it back to whatever object you start. Okay. So this is a forward in time stability result. It's the first stability result for this kind of class of problems. And in particular, it's a stability result of each individual one of them. Okay. So you have a huge family of Penrose stable objects, and these smooth, small, highly regular, and so on perturbations. Say if you take any one of them, you disturb it very slightly in a very highly regular fashion, you converge back to where you started from, and you can describe precisely sort of the remainder of the perturbations. Okay. So it's not somehow a family where you converge from one to the other, although of course in general you might expect such things to happen, but this is just not in the reality. Okay, so all of these objects are individually stable. criteria that are written here, namely highly regular perturbation, is actually a necessity. So shortly thereafter, Lin and Zhang show that if you're not particularly regular, you have nearby stationary solutions. Okay? So in low regularity, so this is WSP, S not too large. Larger than 1. So this kind of low regularity, you have solutions here, smooth, general, stable. There exists DVK waves. So, in particular, exact stationary non-linear solutions. They also showed that there's some sort of threshold beyond which these kind of objects do not exist. So they also showed not anymore as soon as your HS for S larger than 3.5. Just mention that this is all dimension 1 in this particular case. But so they show that as soon as you're regular enough, you do not find these kind of objects anymore. But between the extremely high regularity here and the regularity there is a huge gap. Okay? So technically speaking, the regularity there is something that's almost analytic. Here you have some sort of finite open space after which we do not know these things exist anymore. We just know that if you're low enough in regularity, you have solutions which do not exhibit lambda damping anymore. So there's no stability, you just leave the next value you started with and you end up elsewhere. Okay? So there's no sense in which you could say the result of Moore and Vinani could be extended to any low regularity perturbation. It's necessary that you look at highly regular things.
I'm a little bit confused because D equal 1, I mean,
I think it was a matter of the construction. It's not. It can also be constructed in high
there's
dimension.
no plus, I mean, there's no Coulomb in that sense. I mean, what is the corresponding? I thought this has all to do with the
Yeah, so you can construct it also for Coulomb in 3 dimensions. I think the original work was to construct solutions where you solve Laplace equations. Some boundary conditions. So you can also do it in high dimension. This numerology I've given refers to the one-dimensional case. It's a perturbation argument basically, where you say a bifurcation argument, so where you bifurcate away from Maxwellians to say you find nearby other stationary solutions if you know enough. Question?
And so this was something about the design are these solutions unique also?
Yes, so this is a well-posedness forward in time. You have so much regularity that it's locally well-posed, globally well-posed problem, and then using the side example, you can see what doesn't work behavior. Yeah.
So before we mentioned it, but I missed it. So does the S above is less than 1 plus
1 over p
1 over p? Okay, and then for S greater than p5 is
in HS. So there's some rigidity, which tells you that if you have enough regularity, for some technical reasons this is in that too, if you have enough regularity, then it's not anymore possible. So this hints at the fact that this could be a sharp-ish thing. Yes.
equal to 3 half.
Not that I know. But I'm not an expert in the bifurcation theory. So the main point of the story is the topology really matters. Whether there is nonlinear stability or not is really a matter of the function space topology. It's not something you can decide by just saying that we look at one equilibrium and that anything I do to it is going to be stable or not. It really matters of the function space topologies. There's also some more works, one by Russian, that goes in the direction of trying to show how the justified how big this regularity should be. So somehow more quantified, some sort of result of instability. Again, forgot what H was, but maybe H to the 100 or something like this. So something that tells you if you take a perturbation, even in a highly regular Sobolev space, in a high index Sobolev space, you can move away a large amount from Sobolev. There are also constructions to say that the objects you can construct here, they can be linearly stable, so they can play the role of attractors and so on. So, like I said, the point is a very rich function space topology behind this question of nonlinear stability. Now, there have been many follow-ups to Muro-Villani, so there's some refinements. Of the work of Muro-Villani. The first one is one that's inspired by parallels in fluids, work of Perosa and Masnudi and Muro. It's in 2013. So they simplified the proof a lot. And they also said, okay, we can do this in S regularity, where S is larger than 1. So some exponential class of regularity. Discuss this maybe later, it's a technical point. Then the proof was even more simplified by Dinh Thi NGUYEN and Gorniansky in 2002. So they did some further simplification in the same function space, just again some simplifications, and then the result in what's believed to be the sharp space, where we again simplify S equal 1/3, is a joint work with collaborators earlier this year. So it seems that at some point, or in some way at least, this story of Muro-Villani started is now very much refined. It is also something that is, I guess, by now surprisingly accessible. So it's a very famous work, but you can really understand it in reasonably short papers nowadays. The methods and I think the insights gained since are really allowed one to get a much more robust understanding. There's also many extensions of the works of Muro-Villani. I guess the natural thing is to think of other types of equations to change the interaction kernel a little bit. Then, so if you don't look at exactly Coulomb anymore, you have a much larger class of Penrose stable objects. Or if you look at then more general kernels on other domains. So in particular, you can consider dynamics of what would be typically called screen interactions. Or the dynamics of ions, so where you have sort of a nonlinear Poisson equation instead of this, and so this is even possible then on RD, where D is larger than 2. So again, this here is something that starts with and then there are nonlinear works also for the ions by Antoine Covelli, PhD student in Michaela. There are, okay, so probably I'm forgetting some of the string interactions here. So the dimensional 2 case, the Chinese group. So there's many extensions in the direction of different kind of kernels. Still somehow Penrose stable. Okay, so the spirit is still Penrose stable, so it's extensions of Muro-Villani, I should say. Then you can also ask yourself, can you construct always solutions, but to what extent can you construct solutions that behave in this fashion? So you can solve a final data problem in some generality in exactly this setting. So this is work of which we have an expert in the audience, Stefano. So that's But so you can understand this in large generality, and there's extensions to many other models, further models. So there are models where you have a limited amount of interactions you can have, and you can have even without general stability, similar results. There are works in mathematical biology, or active and passive swimmers. So there's a lot of things that I cannot really adequately describe. There's also more work in this direction of understanding what exactly instabilities are. So it's a question of so-called echo chains. So let me just refer you to the bibliography. Yes?
For screen interactions, we also have instabilities in case of low regularity.
Not that I know of at this point, but I would imagine that's something you would love to do.
Okay, so something to do with the long range of velocity.
No, I don't think instability is the long range feature. Okay, but so let me end this discussion here. But I hope it's clear that there's a lot of things which are really not understood, right? So this is a very restrictive topology in which you understand nonlinear stability. You have some counterexamples, but in general, the dynamics are supposed to be much richer, like in all of these problems, right? So it's a ton of open questions. And the story of R3 is even worse in some sense, in that really there's only one example so far for which we know nonlinear stability. And it's the example I wrote down from this puzzle. The only nonlinear stability result concerns this guy on the nonlinear stability. Years ago. Right? The dynamic at the level of the macroscopic unknowns is the thing that's described there, right? So the dynamic of oscillations. Let's say of rho is this mix of vacuum plus oscillation and damping, like it's written in the linearized case. But the dynamics of the function itself, the distribution function itself, are again free scale. So in the results of Moore dynamics, we have so much regularity that everything decays exponentially fast at the macroscopic level, and the phase space unknowns they behave like free transport. In this result, nothing decays exponentially fast. You have the dynamics that you have there, which means there's some polynomial periods. But the underlying phase space distribution still has the free transport on top. Okay. I guess I said it a few times, but let me say it again. There's no role for high regularity here because it's a low frequency question, these dynamics. You cannot, with high regularity, you don't gain anything. The dynamics are something different. And in fact, they are, well, okay, clearly they depend on this MP, but they're also different from vacuum. So this is unlike the case where you don't know. Okay? So in the results on the torus, whether you perturb vacuum or the Maxwellian, it's the same thing. Any perturbation will behave the same way. It will lead to exponential decay once you have enough regularity initially. Here, the vacuum in 3 dimensions behaves differently. So the vacuum in 3 dimensions, as I guess many have guessed, there's long range corrections as what's known as modified scattering. So you do not have free scattering dynamics. So in some sense, in the 3-dimensional space, this object is really more stable than just the vacuum. Good. So questions about the overview of nonlinear results? Long overview. I will give some context, but of course it remains somewhat vague. Okay, so let me maybe just try to make some comments about some of the points here. I cannot really give you the nonlinear proofs. They're much say something about the formulation of the nonlinear problem, and then point out some aspects here there about various of these results. So let's get back to formulation of this problem. Yes.
So the size of the poles, at least the more given was I think for both verification and for us.
Yes.
I don't know about the other results.
So there's this funny thing that is still true that as soon as you have interactions of perturbations, it doesn't matter which sign they have. But it does matter in terms of the equilibrium you're perturbed. So the Moore and Villani result can deal with perturbations interacting attractively or repulsively with each other, but you need a sign compared to the for the generally you need a sign when you think about interaction with the background of that perturbation. So, but it's also true that here, if you assume that you repulse from the background, but the particles between themselves they attract, it doesn't make a difference. The important feature is the interaction with the background has a certain sign. The reason is that your dynamics, some point there's a plus sign. If it's not a plus sign, but it's a minus sign, then things change. Your poles change. You get what is known as Jeans instability in computational physics. Okay, so how do we set up this problem? Right? So, in some sense, the formulation goes like I sketched it to you for the linearized problem. You have two steps. One is the dynamics of the densities, and then you derive from the dynamics of the densities the dynamics of the underlying phase space unknown. So the first step is dynamics of rho. And the second step is the dynamics of the phase space unknown. Right? So if you know the dynamics of rho, then you also, of course, know the dynamics of the force field, the dynamics of potential, and you can derive the underlying dynamics of the distribution function f. Now I conveniently wrote this equation in the linearized case, and I appeal to your imagination that the function h is just some initial data, right? For the nonlinear problem, it's just going to be more than the initial data. It's going to be some self-interactions in addition. Then the way you solve your problem is you write down the formula for rho, but h is not again something that you're given, it's something that depends on rho, and you can run a bootstrap argument. Okay? So a nonlinear version of the Volterra equation in the bootstrap deals with the dynamics of rho. Nonlinear version of Volterra equation. You cannot solve it explicitly, but you can bootstrap argument. You can bootstrap argument. So for those not familiar, this means you start with some initial assumption that you can show is true for a short amount of time. You have a local robustness in some class. You show that you can prove certain estimates for a short time, and then you show that actually if these estimates hold by continuity, you can prove them and extend the time on which they're true. Yes, the continuation type of argument is very familiar to everyone in PDs, and not then maybe we can say something later about it. The second part then is to derive from the dynamics of T, the dynamics of the underlying dynamics of F. So I wrote the linearized version of the equation, and last time we said how do we get the dynamics of F? We said, well, let's just take the gradient x times gradient m0, put it on the right side, and look at it as a forcing curve. Once we know the gradient of phi, it's just some given object, right? So I'm going to again write the equation as something that is a transport in F. Now in the nonlinear equation, this transport of F includes the transport in both location x and velocity d. And then it's some given object once I have solved type 1 of my So this is the linear thing. once you know the macroscopic dynamics. Now, how do you solve this? Same story as usual. You look at the characteristics, right? You look at backwards characteristics of this problem. It's now not anymore just the fact that in X you transport by V and nothing happens in V. Now something happens in V and you need to account for this. So the natural thing to do is to look at the backwards characteristics. So it means you look at functions, capital X, that depend on two times, the final time and let's say the time times, S and T. You say, you give yourself the fact that at some time, X location is just X, the V location is just V, and in between you solve the characteristics here. So it means that the time derivative in the time that you're evolving in S is the velocities, and now instead of the velocities being just zero, like in the linear case, well, you see this. This is all the functions between X and V, so you find the points, right? So it just says, if you look at the motion here, assume you end up at a certain point. Let me draw it here. Let me say you end up in a certain point with a certain, so there's some X with some velocity, right? The linear characteristic will tell you backwards, you just go along this line. This is your velocity. The nonlinear characteristics will be saying, okay, there's some influence you have on the velocities here, so maybe you don't arrive exactly there, but instead you have some sort of deviation from it. Okay? X and this would be the different V's. Once you have these backwards characteristics, you can solve for F with this given moment. Okay? So in particular, the left-hand side of your equation is just the derivative along the characteristics. That's how the whole thing is set up to be. Right? This is exactly the left-hand side of the equation. Maybe call it star. This is exactly the left-hand side of the equation star, and what you get is the right-hand side. Now the right-hand side is minus gradient x phi evaluated at the base. And you dot the gradient b and 0 at the velocity. Okay. I'm writing this in detail because we get a nice formula at the end. In particular, you'll see that this is exactly the time derivative of S. The time derivative in S of V. So here, there's a derivative. So this is precisely minus the derivative of just this and 0. So if you integrate, you get that your function at the point x dt is equal to the initial data that you move from time 0 to time t. Plus the integral of this, right? Now this is a formula that is very instructive. And it tells you exactly how you accomplish pi 2, right? Assume you know gradient x phi from pi 1. You can solve the characteristics with just an ODE. Once you know this ODE, you just plug it in here, you get the function f. So it means once you know the dynamics of rho, you can really understand everything about f and these nonlinear data equations. So something where you can plug in things that depend again on the macroscope. Okay. It's also instructive in the following sense. How does your phase space unknown move? Assume M0 is just 0, there's nothing there, it's just vacuum. This is gone, right? Then the only thing that happens is that your initial distribution gets rearranged a along these nonlinear characteristics. Okay? So this is a dynamic of rearrangement. This is a dynamic of rearrangement, again, with some flow that is in fact phase-space volume preserving. You understand it perfectly well. Something that conserves all the p norms and so on. This part here is the interaction with the background. This is where you see the effect of n0, and it is where you see that the function, the distribution function f itself, so the particles you have, it taps into this reservoir of n0, right? So this is where you see that there is some exchange with the background. In particular, you cannot say anymore that it's just a rearrangement dynamic where all LP norms are conserved. This is an infinite velocity, infinite speed of propagation effect, where if you even start with some local perturbation, immediately it can trigger some global changes in the velocities. Okay? So it's really something that is very clearly not just a transport equation, it's the equation near m0, and you see the exchange with m0. Right? Okay. Okay, maybe there should be a minus and a plus. Modulo science. Okay, so maybe it's not worth spelling out the nonlinear Volterra equation, but you can see what will happen if you have a right-hand side. Whenever there's a function f, you can plug in this quantity, it becomes the macroscopic analysis, and it allows you to close sum. Okay. Let me maybe use this occasion also to make a comment that I already made verbally before. Let's assume you look at indeed at the case of vacuum, right? So so just a remark from this, right? So remark. Let's look at vacuum in part 3. So n0 is just 0. Let's look at the same formulas, right? If there's no n0, there's no point doing part 1, and you can just view everything as a closed dynamic on phase space. Maybe not so important how exactly you do it, but so vacuum in n0 is equal to 0, and x equals part 3. You remember that what we had conjectured from just the free transport dynamic was that if you look at free transport, the function rho, which was the integral of x minus dv and dv, right? We said this should decay like t to the minus dimension. Minus 3. Okay? 3 dimensions. So it's a change of variables, nothing else. We derive from this the fact that the force field gradient phi in free transport should be like t to the minus 2, because any inverse derivative is related to the powers of t squared. Okay? So this was chapter 3.2, if I remember right. But so if you ask yourself, is it possible that this is the right picture near vacuum? So if you ask the sort of question that we've been answering yes in various shapes, namely, is the linearized dynamics a good model or not? Then you see that for vacuum it's not. Okay? So this is the linearized dynamic, if you want, near vacuum. So the question is this consistent with nonlinear dynamics? So is free transport the thing that you see asymptotically in vacuum? The answer is no. Why not? I think you mentioned it before, maybe. Okay. So in vacuum, what will happen? Let's look at the formulas we have. Let's be very crude. The velocities are going to decay. Right, so ds of v of s and t is going to be like s to the minus 2. Right? So integrate once, I know the velocities are like s to the minus 1. I integrate now to understand how my particles are moving. I get the fact that these things, they are locked. Okay? So this is very sketchy in the sense that there should be constant corrections, right? So here, the velocity should be some velocity 0 plus this s inverse, which means there's some s times v0 plus some x0 for any given initial and so on. The point is, this is free transport, this is the nonlinear correction. So because of this critical nature of the Coulomb interactions in 3 dimensions, if you look at this formula, you know that here there's going to be logarithmic corrections. So you cannot assume that asymptotically everything is just free transport. So, in fact, there's a theorem that tells you asymptotically small perturbations of vacuum in R3 have this kind of behavior. Okay? Small, smooth, localized perturbations. Vacuum undergo what is known as modified state. Okay, so meaning that if we look at a solution, if you look at a solution, this is free scattering, it behaves like a free transport solution. It gets modified. There's a log term, and there's some object which depends on the velocity. It's the asymptotic electric field. Sorry for the small figure. There's some object that tells you that the different velocities and so on. Right? So this is modified scattering. You can quantify things, you still get the kind of decay at the asymptotic amounts, but the actual underlying dynamics of f are different. Small smooth here also means maybe H3 with some localization, so it doesn't require that very. So the vacuum in R3 is really different in terms of phase space dynamics as than the case of the. So maybe this is exactly Coulomb. So here you see that if you did something else than Coulomb, you would get different powers. You could make it worse by doing something more singular, and then the corrections would be even bigger. Actually, yesterday there was a paper on archive about exactly this case. So any polynomial correction would be something more singular. If you make it less singular, then you get something which is integral, and the corrections here just end up being some integral contribution, again, free scattering. So in R3, the Coulomb dimension is also critical in terms of this.
The long range is not short.
This is long range. But you can exactly. But if you make it even longer range, then you get longer range.
Singularity means in the sense of not decay.
Exactly. So singular in the sense of you have some object where the decay you get is not time.
Yeah. So that's the focus on that.
Exactly. So this is universal. This is dimension, and what you do here depends on the law you have. Okay. So I cannot really. Okay, I cannot really cover all the nonlinear topics I wanted to say something about, but maybe let me make one remark that is worth looking at. If you're interested in understanding why this high regularity is needed and what exactly the high regularity statements are, there are some review articles. There's this review article that I quoted, which have some heuristics for what happens in this question of nonlinear stability on chloride. And basically, what happens is a version of this unmixing iterator. So it's the fact that if you start with some distribution which has many different frequencies, then these frequencies, they start out somehow small somewhere, and then after some time they create an order 1 contribution. And you can have a chain of such frequencies which leads to some normal inflation. And there's a heuristic that tells you that the sharp regularity threshold should be determined by 1/3. It's a heuristic. It's only here in the related context in fluid dynamics where this is happening. So maybe let me not spend too much time on this. See the review paper of Philosophia. Let me instead make some comments about how it is possible that these objects, so this object, I should say, this object is somehow more stable than the vacuum. How is it possible that you get better information, or stronger stability at that level, the phase space distribution than just vacuum?
Why do you say that this is not a solution, but it's a unification of that? But what role does it play?
So it plays several roles. One role that it could play is if you look at what kind of quantities diverge as time goes to 50. You have these logarithmic contributions that mean that if you want to understand the things, if you look at, say, natural unknowns for a problem, if you look at things where you can easily know what you can account for, you look at things that incorporate the linearized structure, like using vector fields or the chain of unknowns, then in these frames many things diverge. Whenever you have velocity regularity, you get something that's much more divergent than if you're free scatter. So it is more singular in this sense, and in particular, it's believed to be, it is harder to solve final data problems because you need to incorporate many more things if you don't know how exactly to incorporate them. So you don't know this fraction a priori, so if you want to solve it from infinity, for example. Okay, we can debate whether it means it's more or less stable, but in particular, there's nothing you can do to improve these rates. Whereas in some sense, the rates in practice are actually better here. So that's what I mean more stable. There will be more decay of the macroscopic unknowns, or there will be this additional component of oscillation.
But you cannot say that there is no down in this case because of this.
So I think I have not yet seen anyone that claims that this is lambda damping, because the uses of lambda damping so far have been restricted to things related to lambda and things which are phase mixing. Phase mixing means dynamics as a linearized problem, which this is not. Exactly. It's almost, but it's not. So it's a nonlinear stability result that falls, I think, smoothly into the realm of all these stability results. But it's not lambda damping as far as I know. So let me maybe state the theorem in this case is take a small, smooth derivation, so that says that this sum epsilon larger than 0, the perturbation is smaller than epsilon is close to the base. So if some initial function f0, let's say it has some decay velocity, r5, some gradients that is also put. Just put one gradient in. W1 in x and b. Explicit. Assume you have enough regularity in velocity and space. B is less than epsilon. Say your A is enough between 0 and 1. So if this is small enough, then you get a unique global and time solution. The Poisson system, which is of the form the Poisson equilibrium plus the perturbation. The initial data of the perturbation are these initial data. And, well, you can say what it does, right? So you can say the gradient field, it decouples into two pieces. It has, let's say, a static part, and it has an oscillatory part. And we write it again as a complex thing, but on the right side of cosines of various points. That's a real complex kind of object. So there's these two pieces where the first piece decays almost like T to minus 3. So almost a little bit more. And the second piece doesn't decay quite as fast. Okay. So this is what I meant in some sense by more stable. Sometimes you have a gradient force field that decays faster than you would have in the vacuum case. And you have something which decays less fast, in particular less fast than in the vacuum, but it has no switch. Now, you also know what the distribution does, and in fact, what I described as free scattering and no logarithmic corrections, just this object itself. Okay. Now, there's many, maybe some more comments to make, in the sense that on R3, these dynamics always are associated with some sort of loss in topology, in that what you assume here is not the same topology that you have the convergence statement in. In particular, you cannot get this to be a convergence in a lot of in higher degrees of velocity or in other weighted norms. It's really something that is somehow a weak statement. When you do the same thing for the lambda damping of Moreau and Villani, basically whatever you assume here, with some small loss associated with time, can be carried over also there. So it's much more like a semi-linear problem, whereas this is a quasi-linear problem. So the Moreau-Villani argument says you assume some sort of analytic type regularity, you get convergence in analytic type models. Here, you have some finite regularity clearly, but you still lose some. I hope the contrast between these statements is clear. So let me just finish with one comment that tries to say, okay, how can it be that the decay rates are so slow? One is fast, this one is slow compared to vacuum, yet you get this kind of free scattering pattern. Yes, it's a guessing game with one very clear touches. possible that we get this free scattering despite the decay being slow. Yeah, nothing like that. The fact that you have oscillations. So in practice,
Excuse me, man. Please do sound first time is S is whatever or is creating special S? No.
it's supposed to be a 5. It's a 5, right?
And
Something that's just related to something a little bit faster than the object that you're perturbing. The object you're perturbing was this MP, which is became like b to the 4. I assume this is a little bit smaller. I think in the actual statement is 4.5. I think it's a little bit faster.
what do you mean by in one precision and in B and C
Oh.
precision?
So something like other questions? Okay, so just to reiterate and spell out what Benjamin said. So I raised the thing with the characteristics, right? But the only way to get this modified scattering is to say that in this formula, the characteristics actually asymptote to something here which does not have more than the linear correction. Right? How is it possible that you do not have these corrections here? So in this heuristic, right? What changes? It changes that you integrate an oscillating function. Right? So let's do just the first step. So this is still rough, but let's say this we said is a gradient x phi. Right, so you write what it is. It's an integral over time. So time tau s of this function. Now I plug in what it is from before. This is two pieces. Static piece at time s and this oscillatory piece. Proper unknowns is s. Looking at time s. S, right? This object here we said behaves like s to the minus 3. Okay? So the contribution you get from here is going to be much better already, right? So this is something that even if you integrate it twice, it's perfectly integrable. So this is twice integrable. So never mind this part. Here you're integrating an oscillating function, which means that to reading order, let's say you pick up the boundary values, right? So this is smaller than the integral of its size. So this object would actually not be what you would expect. It's not, so this part is s to the minus 2, but it oscillates. So if you integrate, let's say from 0 to from s to t, the function e to the is s to the minus 2 plus ds, you don't get s to the minus 1, right? You get tau. Everything is tau, like the only integration variable. The integration variable is tau. Integrate from s to t, tau. The point is, this is not the size, but it's one order better, basically. Right? So this is almost again only s to the minus 2 plus, because it oscillates. So it means once you integrate it once more, you'll still have a finite correction. So this is something that I guess is a very basic version of what you would call a normal form. This is the derivative of itself. The derivative integrated. But it's actually what underlies much more of the nonlinear analysis. Okay? So if you remember the function that we had, it was the delta at time from 0 minus 1 minus, let's say just e to the minus k times t itself is also time derivative. Means that when you look at your solution formulas, actually the splitting that I suggested is not the right splitting for all cases. You should also make use of the fact that in the green function itself there is an integration, right? On the first line here, I'm integrating the green function. I have choices in integrating the green function if the green function itself is a time derivative. Moreover, the function I'm integrating here is not just any function, it's a function that has some sort of kinetic structure, meaning it's translating by t times v, like my initial data. So there's many more of these ways that you can exploit the oscillations using normal form methods. And so this kind of oscillation is made simple for their characteristics. In general, in the proof, it has a lot of power. So you can use it in many ways in different places. And so the oscillations are really crucial. Okay, so non-unistability without these oscillations is not really possible. You will not have enough decay or anything like that. Okay, good. So maybe let's just stop here and you want to some kind of questions. So it's the best thing that you could have, in the sense that you, in the green function, you have one piece which is, let's say, the vacuum at high frequency, which you cannot escape. In the vacuum, high frequency has this t to the minus 3 decay, which is just the decay of density. There's some technical loss, which means I don't actually get the t to the minus 3, but it's not possible to have exponential decay. Even if you start with a Schwartz function, it doesn't value anything. Dimension is the thing that turns.
And entities like this is like very special function.
Yes.
It doesn't seem like this. Do you know any other class of function that you expect from one?
Yes, so I know many things that I expect, I don't know many things that I can prove. So, I would say that this mechanism that I'm sketching here is representative for a certain class of similar type equilibrium in the sense that they're still pretty fast. And this I hope I can prove soon. The point is that here there's many things that make this much more explicit and easy to access. For example, oscillations just have fixed frequency.
The solution is the same as the sine phi that you have in the green function.
It's exactly that. But once you change away from this, you have these corrections where the oscillations depend on the frequencies. So they become really dispersive in nature. Now there's still 1 plus something, so whenever you have a 1 plus something, you can still do normal form if the something is small, right? So this argument of oscillations, it didn't really use that I have exactly e to the I tau. If I'd been 1 plus epsilon, it would still be fine, right? So the thing that I can extend is probably to some similar class function, but what I get is that decay is going to get weaker and weaker. There's some sort of boundary case, which I'm trying to understand, which is something where you have much less decay, which is a 3/2 decay, which is what you would naturally get then for anything that's even more decay, just a natural sort of dispersive decay. But if you want to understand what happens for, for all of these other much thinner equilibria, then things get much harder because the damping curve is much weaker, right? So this object here is going to be k to some high power, meaning a small frequency is not going to have to be very much. If you consider the max value, it's very low. There are many other difficulties associated with doing this setting. You can also look at it in other settings, but it's a risky version and so on. So yeah. I think this is the beginning of hopefully something longer, and I expect many of these things to be stable. You expect all of them to be free scattering, heuristically based on this kind of argument, but there's actually no proofs to be stable. Right? So it's a start, and we'll see.
So in the Taurus case, the decay depends on the regularity, right?
Yes.
So this sort of decay corresponds 1/3, corresponds to this t minus 2 over there, or
So in the torus case, this can be anything. This could be e to the minus 2 if you want.
depending on the regularity,
Exactly.
Then maybe there is some, I mean, you can move it up to rise to equal to 1/3.
Exactly.
And that was the corresponds to this P minus 2 or not?
No, it doesn't have anything to do with this P minus 2. It has to do with the fact that in the let's say the nonlinear versions of your argument, so you have something which is your density. It will have a bunch of pieces. It will have everything that's from the background, which doesn't matter initial data and so on. And then it will have some nonlinear term, which is again the density at some other frequency interacting with the unknowns. F. Yeah, and integrate with some L and so on. So there's some nonlinear terms. Yes. And the claim that why this has to be 1/3 is not proof for this case. But the claim which it has to be 1/3 is that there is basically a chain of echoes that says this function is going to be very well localized, so it will trigger precisely one mode here. So this one mode is basically so this would be interacting with a mode which is if I remember it right, something like this. So you have a mode at a higher frequency at an earlier time, is less than 1, that will inflate what happens to this mode. So basically you take some starting mode, you excite lower modes at a later time. And this is a cascade, which every time leads to some inflation given by the terms in this formula. And if you heuristically sum up everything that can happen, you reach something that says there needs to be some exponential there's some exponential inflation along these echo chains, which scales like then inflation is something that scales like C constant C e to the. This is something that scales like e to the C to the 1/3, let's say, constants times what you had at 0 with the right times and stuff. So roughly speaking, it says that your initial data get inflated by a certain factor, and then at the time in these kind of echo chains, so you need to be able to absorb this kind of factor on your initial data. So it's a nonlinear interaction of these kind of inflections. So this is the model, the heuristic that's discussed in the review paper by Bedros. It's a complete heuristic, and the only place where it's proved is for corresponding 2D fluid model. So 2D implicit damping correct. There's a proof by Deng and Smoothie that says that this kind of thing actually happens in the sense that if you have any little bit less than this regulator in data, you can go from something that size epsilon to size epsilon inverse in time 1. Doesn't mean that you know what happens later, but it just means that this kind of stability where you constrain yourself to some epsilon neighborhood is lost. It's a feature of precisely these nonlinear